looks like everybody's probably back. Well, maybe missing one there. There she comes. Okay, well, anyway, the moment you've all been dreading has arrived, which is the first lecture from me. And I better set that down there or it'll get turned over. So, anyway, a little word of warning. My hearing is failing, typical of old guys. So if you ask me a question and I ignore you, that means I didn't hear you. If you ask me a question and I give you a perfectly good answer to some other question, that just means I misunderstood you. And that's especially true if you're a woman with a high-pitched voice. So anyway, I'm not offended if you raise your hand and say, no, that's not what I asked. We'll figure it all out. Anyway, this will be fun, although mostly it'll be fun for me, maybe not so much fun for you. So today we're going to talk about, first of all, the volume scattering function, and then along the way we'll look at a lot of data, and then we'll talk about models for absorption and how those things get used. So first question is, well, I guess actually we have our little flow chart here, and Colin has been beating on absorption in several lectures. You've had a bunch of labs on measuring absorption. Emmanuel talked about beam attenuation yesterday, and then I'm going to start out talking about the volume scattering function here, and then the things that you can derive from that. If you notice, if you know absorption and the volume scattering function, those give you everything else that people commonly use. Total scattering, backscattering, so on and so on. And so by the time we're done with me today and the lab on scattering this afternoon, we will have checked off the box and you will know everything there is to know about inherent optical properties. And you remember that those are things that describe the optical properties of the medium. They depend in general on concentration, size distribution, composition, what the things are made out of, shape of the particles, and so on. And they do not depend on the light field that's in the water. So you can take a sample, go in the laboratory, measure absorption, measure scattering. Okay, so here's a question. Why is scattering important? Well, here's what the world looks like if you have scattering. What would the world look like here in this picture of the sunset at the Oregon beach if there were no scattering? What would you see there? Yeah, you would see the sun's direct beam attenuated by absorption, and that was it. But because everything else in here, the reflection off the sand, the scattering by the sky, that's all sunlight that has interacted with an air molecule, got redirected towards you, and now you see it. So I think that's the real answer as to why absorption's important, or scattering is important, right there in that figure. And scattering simply means that the light changed direction, and it might also change wavelength. And there's three places in the ocean that scattering occurs. At the sea surface, light can reflect off the surface, and that's a change of direction, so that's scattering. It occurs within the water when the light interacts with a water molecule or phytoplankton or a bubble, and it changes direction, so that's scattering. And it also gets reflected off of the bottom if you're in shallow water, and that's more scattering. So some people, when you read the literature, they will talk about like this being surface scattering and this being volume scattering, but it's all really just scattering. And in this lecture, I'm only going to talk about the scattering by the things that are in the water. Later, we'll have a lecture on reflectances by hard surfaces like sea bottoms and seagrass leaves and so forth. But anyway, that's where we're headed today. So, other reasons why scattering is important. Well, it's the scattering that determines the angular distribution of the radiance within the water. If there were no scattering, sunlight would go in the water and it would just keep heading straight down. So it's the scattering that bounces it around into all directions, and that means it's the basis for ocean color remote sensing. It's light that got into the water, got scattered back upward, and got out, and you observed it, and so away you go. There's a saying that a little bit of absorption goes a long way if you have a lot of scattering. Well, that's this path length business. If the light's bouncing around a lot, whether it's in the ocean or in your cuvette, you're simply giving it more opportunity to be absorbed. And as we'll see in a later lecture, scattering messes up visibility. When you go outside on a hazy day and you can't see the mountains very far away, that's not because the light's being absorbed, it's because it's being scattered, and that messes up what you can see. Emmanuel has been telling you a little bit, and will tell you more, that scattering is a diagnostic for particle properties, because scattering depends on size and shape and composition. So that tells you something about the particles. And from my perspective, it takes a lot of math to do scattering, so that means it's a lot of fun. Okay, so today I'm going to review the basics. A lot of what Colin gave you yesterday I'm going to tell you again, but a little bit different viewpoint, and maybe the second time it'll make a little bit more sense. Then we'll talk about the volume scattering function in considerable detail, and maybe then we'll take a 5-minute break, and then we'll look at data for scattering by different kinds of particles, and then taking that data and putting it together and getting models for scattering that you're going to see again when you run hydrolyte, for example, or any time out in the real world. Okay, so just once again a little review here. You've got a particle, there's light coming in, electromagnetic field interacts with all the charged particles in here, and they re-radiate, which just means that the light goes out in all different directions. And you did this kind of thing in the lab, and you could look around at the front end of the tank where the light's coming in, and it looks brighter than if you look from the side. So in general, there's more light being scattered in the near forward directions than there are in the backward directions. And if you look into the beam, which we don't recommend with lasers, but it's okay with flashlights, in general the light's going out in all directions there. And if this is a flashlight, it's probably going out equally in all directions. If it was a laser light, it's going to be scattered much more strongly in some directions than in others. So anyway, that's just the basic idea there. And if we think of sort of, drawing a line that shows here's really strong scattering in this direction and less here and less here and less around here, and just kind of think we've got a little curve here that maps how strongly the light is being scattered in different directions. And if we assume the particle is spherical and the incident light is unpolarized, then this will be azimuthally symmetric. In other words, in this figure, there would be equal amounts in all directions if you're looking into the beam, and this is azimuthal angle, and this is a polar angle measured from this direction around to the backscattered direction. So for the moment, to make the math easier, we will assume that we have a spherical particle here and unpolarized light, so we only have to worry about one scattering angle, which I call psi. It's measured from 0 in the forward scattering direction or no scattering, 90 degrees at right angles, and 180 degrees for light that is exactly backscattered. And that's just usually called the scattering angle. I always use psi for the scattering angle. Yesterday Colin used a theta, other people use other things, and it's only confusing when in a paper a person uses theta for the polar coordinate in their coordinate system, and then they use theta for the scattering angle, and you don't know which theta they're talking about. That's why I always use theta and phi for coordinate systems and psi and alpha for scattering angles. But anyway, just pick it however you want to do it, and stick with it and make sure you know what you're talking about. So if we think about taking this little curve in space here, and then just kind of unwrapping it and plotting it from psi equals 0 around to 90 around to 180, and plotting it as a curve there, well, that's your volume scattering function essentially. So it's just a way of turning this kind of cartoon figure into a curve on a graph. Nothing fancy. In practice, you've got let's say your sample has got phytoplankton, it's got all kinds of their things in there, they're not spherical. And so if you wanted to say, what's the volume scattering function for diatoms, for example, and you've got some particular species and they're whatever shape they are, well, they're not spherical, but you just kind of think of, if you made measurements and you average these guys over all of their orientations, and then they're not exactly one size, so you average it over some small ones and some medium-sized ones and some big ones, and just kind of take all of those individual volume scattering functions and add them all together and average them and call that the volume scattering function for diatoms. That's what's usually going on in the literature when you see some statement that we measured the volume scattering function for some kind of particle. So in theory, the VSF is defined for one interaction with a single particle, but in practice you think of averages over particle orientations and particle sizes, and then you go from there. So you've kind of gotten an equivalent diatom, if you wish. And that usually works pretty well, but it's not guaranteed to work. Colin mentioned solid angle yesterday. I'm just going to go through it one more time because it sometimes is it's confusing, even though it's not complicated. But if you remember, as she showed you here we've got a circle in a plane, and the definition of this angle here is that it's the arc length along the circumference divided by the radius. So that's simply the definition of angle. And so even though this might be meters divided by meters, so angle is really a non-dimensional number, but we give it this so-called unit of radian just to remind yourself that if I say this angle is 0.2, it's a 0.2 as an angle. It's not 0.2 per meter or 0.2 kilograms or whatever. So it's just a reminder that we're talking about this non-dimensional number really being an angle. And of course the circumference is 2 pi times the radius, so you divide 2 pi times the radius divided by the radius gives you that there's 2 pi radians in a circle. Okay, you all know that. Now, for the three-dimensional equivalent, if you had a sphere of some radius r and you have a little patch of surface here, then the definition of solid angle is that it's simply the area on the surface of the sphere divided by the radius squared. So area is going to be, say, square meters, and radius is in meters. So once again, it's a non-dimensional number, but we give it this name steradian just to remind us that we're talking about a solid angle. And ster just comes from Greek for solid. So anyway, the surface area of a sphere is 4 pi times the radius squared. So divide by the radius squared. There's then 4 pi steradians in a whole sphere. And if you want to think of, a particular example, let's say this little area here is the surface area of the lower 48 states of the United States. And you look that up, well, that's about 8 million square kilometers. The radius of the Earth is about 6,400 kilometers. So you could say, well, I'm sitting down at the middle of the Earth and I'm looking out at the bottom side of the United States up there. So what solid angle is that? Well, it's simply the area of the 48 states divided by the radius of the Earth squared. It's about 0.2 steradians. So there's nothing magical about solid angles. It's just if you haven't run across them again, they might be a little strange. And they're just simply a three-dimensional equivalent of a two-dimensional plane angle. But you're going to live with that for the rest of your career in radiative transfer theory. Okay, so how do you actually define this volume scattering function in a way that will keep the mathematicians happy? Well, here we're going to have a little volume of water. It's some thickness delta R. There's some little area here A that is being illuminated by power coming in at some wavelength. And so we really have a little volume of water that's A times delta R, so that's a little volume delta V. Okay, and we're going to assume that this is thin enough that when light comes in, it'll only be scattered once before it goes out, or it can go straight through, or it can be absorbed. But anyway, if it's scattered, only one scattering, because this volume scattering function describes how light is redirected in an individual interaction. Now, you go in the real world, it may be multiply scattered, but each one of those scatterings is described by the volume scattering function. Okay, so as Colin showed here, light comes through, some of it is scattered out into some little element of solid angle, and if we're assuming that things are azimuthally isotropic, then really it's a little ring here of solid angle. So, and that has some little solid angle delta omega. And there's some amount of power here, some fraction delta phi that's scattered into that little solid angle for whatever the scattering angle is. So the definition of the volume scattering function simply says, look, take the fraction, however much power is scattered into my solid angle, that angle psi, normalized by what's coming in, and then divided by this little distance delta r and this little element of solid angle. Now, if you have an instrument, you stop right there and say, okay, I know the delta r, maybe that was 1 centimeter. I know the delta omega of my instrument, maybe that's 0.1 steradians. I measured what was scattered here, the power collected. I know the power that went in, and that's my value for the volume scattering function. The mathematicians like to say, in the limit that you have a very thin region and in the limit that you have an infinitesimal solid angle, then that's the mathematical definition of volume scattering function. And you'll often see in literature there's a conceptual definition, which would be taking the limits. And you read a paper by Howard Gordon, if you take the limits here, this might be written as the second derivative of phi with respect to r and with respect to omega. But then you read an instrument paper, you get what's called the operational definition, which means how do I define this with things that I can actually measure in the laboratory, and forget what the mathematicians do. So I do the limits, Ken Voss stops there, and hopefully we both get about the same answer. Now, we haven't had the radiometry lecture yet, and we've kind of been talking about these terms like radiance and irradiance and so forth, which we haven't really explained to you. But there's also another thing called intensity, and that is how much power is scattered into a unit solid angle that's coming from a point source. So if we think intensity is scattered power divided here by unit solid angle, and then irradiance, remember, is power per unit area. So I can actually rewrite this. I can say, look, the power scattered divided by the solid angle, that's scattered intensity, as the radiative transfer people call it. And then if I divide phi by delta A, or by the area A, well, that's really irradiance. And then I multiply by A, that's A times delta R, that's an element of volume. So you'll often see this as being defined as the scattered intensity normalized by the incident irradiance and by the element of volume. So that's why it's called the volume scattering function instead of the distance scattering function or something. But you'll see it defined either way. And of course, whatever units you're measuring power in doesn't matter, they cancel. So this thing has units of per meter per steradian. So the volume scattering function is simply telling you if light's going along, how much is it scattered per meter of distance traveled and per steradian of solid angle in a particular direction, psi, the scattering angle. Okay, so conceptually, once again, not complicated, but if you're coming onto this thing for the first time, you don't have much feeling for what all is going on here. Okay, bottom line, the volume scattering function tells you everything there is to know about scattering if you ignore absorption, polarization, which we're going to do at the start here. And of course, it's a function of both the scattering angle and the wavelength. And the VSF has information on both the magnitude of the light scattering, or how strongly is it scattering, and it has the information on the angular distribution of that scattered light. Now, what's nice is you can take the volume scattering function and you factor it into the scattering coefficient, same thing you've been working with your AC9s, and the scattering coefficient, which is just a single number at a given wavelength and location, that contains the information on the magnitude of the scattering. How strongly does this stuff scatter the light? And then the other thing, the other half of the factor here is called the phase function, and that contains the information on the angular distribution. So when you write that the volume scattering function beta is the scattering coefficient times the phase function, and this is really just definition of the phase function. This thing is per meter per steradian. This guy is per meter, and this part has units of steradian. So this has the magnitude, and this part, which is a function of scattering angle, this has the angular information. And we'll see how that goes here in a minute. So, as I said, if you know the VSF, you can get everything else there is to do with scattering. So, for example, if I take the volume scattering function, I've got light going in a particular direction, and now I'm going to integrate the VSF over all the scattered directions. So this guy, integrating over direction, means integrating over all 4 pi steradians of solid angle, and Colin came up with this little formula that said the element of solid angle is sine psi d psi, and she called it d phi. Well, if it's azimuthally symmetric, the d phi part integrates into 2 pi, and you'll usually see the scattering coefficient defined by this equation right here. So you take the VSF, integrate over solid angle, and now we're integrating the scattering angle from 0 to pi. Anyway, that gives you the magnitude of the total scattering, and of course that's beam attenuation minus absorption. Okay, and then as I just wrote here, we can define the phase function as being the VSF divided by the total scattering coefficient. So this guy now has units of steradian, and so this has the information on both the magnitude of the scattering, or the strength, whatever you want to call it, and the angular part. This now is the strength part, or how strongly it scatters, and this is the angular part. So you could have, let's say, given particles, they would all have the same angular distribution, but if you change the concentration of the particles, you'll get more scattering, and that's reflected in here. So they're, the 2 halves of the total scattering that's going on. Okay, and it's often much easier, as we'll see, that you'll have a phase function for a given kind of particle, like diatoms or water molecules or air bubbles, and then as you change the concentration of the diatoms, you'll keep the same phase function, but you'll increase the concentration, and that'll increase the total VSF. So it just enables you to work with these 2 separate pieces. Okay, people often use the backscattering coefficient, and that means simply integrate from scattering angles of 90 to 180 degrees. That's a measure of the light where it's coming in and it's scattered somewhere back more or less towards the origin. And if you integrate it from 0 to pi over 2, that's the forward scattering coefficient. But it's the backscattering coefficient that matters for remote sensing, because that's the light that went in and got scattered back upward. So that's very important. We're going to be living with that for the rest of the class. There's the backscatter fraction, which is of the total scattering, what fraction is scattered into the backward direction. So this, of course, is units per meter. The backscatter fraction is non-dimensional. And in the ocean, this fraction is typically like 1, 2, 3%, depends on what kind of particle it is and how big they are and all of that. But, you know, just think of this as usually a couple of percent, except for water molecules when it's actually 50%. Then there's something else called the albedo of single scattering, which is the fraction of total scattering to total attenuation or absorption plus scattering. Well, that's also a non-dimensional number, and it simply says if the light's coming along, it interacts with a particle. Now, it can either get scattered or it can get absorbed. And if it's scattered, it goes on its way. If it's absorbed, adios photon, your history. So this is sometimes called the, where did I write it here? The probability of photon survival. So if there's no absorption, the light interacts, all it happens is it gets scattered. So omega naught is 1. It's probability of 1 that the photon lives on. If there's no scattering, then this becomes 0, and if it interacts, the only thing that can happen is that it's absorbed. So there's 0 chance that it's going to survive. But in the ocean, depending on the wavelength, this could be 0.2, it could be 0.9, you know, just almost anything. Very strongly wavelength dependent, and we'll be seeing this guy for the rest of the course. Yeah.
What were the characteristic backscatter fractions you said?
Sort of like 0.01 to 0.03 or 4. So a couple of percent of the light is backscattered and 98% continues on in some forward direction. And I've seen data with this up to like maybe 4.5%, and that was for mineral particles that are very high index refraction, so they really scatter a lot of light in all directions. For phytoplankton, this is more like 0.5% to 1.5%. Okay, these are just a couple more plots of, you know, thinking about what this volume scattering function looks like. So here I plotted a couple of phase functions. So this is VSF over B, units of steradians. And you'll notice Uncle Curt will never ever show you a graph that doesn't have the axes labeled with the units. So if you submit a paper and you suggest me as a reviewer, make sure your axes always have the units there. So anyway, and it's really bad. I occasionally get a paper to review. Axes aren't labeled at all. And it's just like, what is this? Like milk production versus the weight of the cow? I don't know. And I worked with a guy one time, I think he was just genetically incapable of labeling axes. It was just bizarre. He would come into my office and say, oh, look at this great data I've got here. And I'd say, well, yeah, what is it? Oh, well, it's whatever, you know. Well, yeah, you know that, but I don't. Okay, anyway, that's my rant for that. So I just plotted the phase function here. This is on log-log axis. This is log linear, same phase function. And then I just kind of color-coded it by angle, and then I redrew what this looks like as kind of a three-dimensional sphere. So the light's coming along, it's going towards the North Pole, and that's the unscattered direction, and then it's scattered off into other directions, and the equator would be light scattered at a right angle, and then the South Pole you can't see, that would be exactly backscattered light. So most of the scattering is in the very first few degrees. So you go from here's 1,000 and down to 1, a factor of 1,000 decrease in, say, the first 10 degrees or so. So most light is only scattered by a little bit, just by a few degrees. And so you get this concentration of color right here. And I just expanded that. This is 1 degree, 5 degrees, and 10 degrees. It's just this little area here expanded. But you see this very highly scattering red here. That's only in the, you know, a first degree or so. And then once you get out to the backscattered directions, there's it's not constant. It usually has a dip or a minimum somewhere around 120, 30, 40 degrees, and then it may go back up a little bit. So you get this big area in the sort of side scatter and back scatter direction where there's not much change in the phase function, in the shape of the phase function. So that's just another way to try to build up some intuition about what these things look like. And you know, when you were playing in the fish tank and shining a light through, and you went around the front and looked through, you were kind of looking at the center, and if you looked in from the side, you were looking at this area, and it's much, much less bright than when you're looking almost into the beam. Okay, so there have been a number of instruments developed over the years for measuring volume scattering functions. Now, the catch is with, say, an AC9 and the total absorption and the total scattering coefficients, you're just measuring one number. That's hard enough to build an instrument to do that as you're learning. When you want to build an instrument to measure the whole volume scattering function, it has to be able to make measurements over this range of angles from ideally 0 to 180. So now it's like if you had an AC9 for every scattering direction. So you could think of like take, you know, 20 AC9s some way, fix them up so each one would measure a different angle. Well, that gets to be a much more difficult problem, and Ken Voss can tell you all about that because he's one of the guys who has actually built an instrument for measuring volume scattering functions, one of the early ones. And is GASM still up and running?
It's not really running. It's still in my lab.
Okay, well anyway, so over the years, starting with this fellow Ted Petzold back in '72, they built instruments for measuring volume scattering functions. And Petzold actually had two, one that measured the first few degrees, and it was 11 feet long. And then he had one that measured from kind of like 10 degrees around to 170, and it was like this big around and this high. And that's the one Ken inherited. Anyway, we're not going to go into the design of these things. People over the years here, several papers, and I say they're all in the library, but I actually haven't given Sasha my collection of papers yet, so remind me to do that today. But yeah, people keep coming up with a new and better way to measure the volume scattering function. These are all one-of-a-kind instruments. They're not commercially available. There is now a LIST volume scattering function instrument that is commercially available, and it measures, I don't know, it's like 0.1 degrees or something around to 170 in a couple of different ways hooked together, and seems to give pretty good numbers. But you know, if you're interested, you can click on the link there and go look at the details. I'm not gonna bother to spend the time on that since I'm not on commission to sell lists, but it is out there. It also measures some polarization parameters as well. So we're kind of getting into the world now where there will be instruments you can put in the water and measure volume scattering functions, including a couple of the elements of the Mueller matrix. And 10 years from now, that'll probably be routine. Okay, so let's look at some VSF data here. So this goes back to data taken by the instruments developed back in the 70s by this fellow Petzold. And he took his instrument and he put it in clear ocean water and coastal water and San Diego Harbor, which is turbid water, just to see what came out, because this was in the days where these were literally almost the first measurements of volume scattering functions, and nobody quite knew what they were going to look like. So here's the VSF, and here's the open ocean, the coastal water, and the turbid harbor. And you can see for any one of these curves, there's sort of 5 or 6 orders of magnitude difference as you go from small angles of 1/10 of a degree around to a minimum here somewhere and then 180. So just think of 6 orders of magnitude, and then as you go from one water body to the next, there's another couple of orders of magnitude just due to the water you're in. So there's a real problem to design an instrument that you can go throw in any water body, and it has to measure 6 orders of magnitude for a given curve and has to be able to operate in water bodies where there's 2 orders of magnitude difference in the magnitude of the VSF. That's an enormous engineering challenge. Okay, but you'll see a lot of papers that refer to Petzold's data. There it is. And they'll say, you know, I did my simulation using Petzold's open ocean volume scattering function. Well, there's what they're using right there. And it's tabulated data. You can download it in all kinds of places, including the web book here. And this is the same thing plotted on a log linear scale. When you plot on a log scale, you can really see the small angle effects and you don't see much about the backscattering. If you plot on a linear scale, you get a good look at the backscattering angles, which is what's often of interest. And I notice I put here for each of these, if you take this curve, multiply by 2 pi, sine of psi, you know, integrate over 0 to 180 degrees, then you get the total scattering coefficient, which for B, or for the open ocean, was 0.037 per meter and went up to 1.8 for the turbid harbor. So pretty good range of scattering coefficients in these 3 curves. And those are pretty typical of oceanic volume scattering functions, but there's a lot of variability in those things. Now, the idea then came along after people looked at these curves and said, well, you know, these have pretty much the same shape. They just have different magnitudes. So it would be really nice if I could some way kind of take the average shape. So I'll take each of those curves, I'll divide, which were plotted there, I'll divide by their scattering coefficients, and I know the VSF is highly variable. I know the scattering coefficient is highly variable, but maybe they vary in sync with each other so that the shape of the phase function will not be variable. That would be really nice. Then I can put all my variability into the scattering coefficient and I can keep using the same phase function all the time. And that was done for the 3 Petzold curves, and they do lie pretty nicely on top of each other, except if you look in the backscatter direction, that's like almost an order of magnitude variability. And if you look in the forward direction, well, that's a lot more variability. So in the middle, they fit together pretty well. So the question is, well, can you really get away with doing this? And the answer is, here's a bunch, actually 62 phase functions made in coastal New Jersey waters at 530 nanometers. And there's an instrument called the volume scattering meter, was developed by some Ukrainians. They came on this cruise with Emmanuel Boss and Marlon Lewis. They put their instrument in the water. You know, Emmanuel got the data from them, I got the data from Emmanuel, etc. So anyway, here are 62 phase functions measured in what you might think is pretty much the same water. I mean, it's coastal New Jersey, and you know, they measured something over here and then they went over there, and then they measured today and then they measured tomorrow. And so here's the variability that you get in the phase functions. So each of these, they measured the VSF, they determined the scattering coefficient, they divided the VSF by B and got the phase function. And I plotted those up. Well, first of all, there's a funny little kink in the curves here, so that's probably some internal reflection or something in the instrument, you know, hard to say. So I wouldn't believe the physics there, but the rest of it looks pretty good. Here's this average particle phase function for Petzold. So it's what people do is they take their 3 Petzold curves and they, you know, get the phase function and they average it and they say, well, I'm going to call it an average particle phase function. And people use this red curve like it was a law of nature. Well, really, it's the average of 3 measurements made in the 1970s. And it's still being used today. And it speaks pretty highly of these old guys that they got data in 1972 that's good enough that people still use it today. Or more often they misuse it. But anyway, so here's the Petzl average particle phase function, and here's all the ones that were made in this New Jersey water. Well, first of all, notice that's an order of magnitude variability in the backscatter direction. And the Petzl guy looks really great on average. But now the problem comes. You're going to run hydrolyte. You didn't measure the phase function, so you say, well, I'll just use the Petzl one. It's built into hydrolyte. I can pick it. Well, if you pick this phase function and your water was this one, or your water was this one, your hydrolyte predictions are going to be off by a factor of 2 or 5 or something like that, just because you used the wrong phase function. And that's just the way life is. So you really need to measure these things, but there's no convenient instruments to go measure them. That's the state of the ocean sciences today. Maybe 10 years from now, 20 years from now, you'll have an AC9 and it'll have another little thing on the side that measures the volume scattering function, and life will be good. But right now it's not so good. And just keep in mind that even on the shape of the phase function, there's order of magnitude variability even in coastal New Jersey waters. Now, if we go to the Yellow Sea and the Southern Ocean and the Mediterranean, who knows? Even more variability. Okay, so I think I've already said that. The problem is you seldom can measure the VSF, so you have to guess it. And if you guess right, life is good. Hydrolyte's going to give you good results. If you guess wrong, hydrolyte's off by a factor of 5. You're sending me emails asking what's wrong with hydrolyte. The answer's nothing. It solved the radiative transfer equation for the input you gave it. You just gave it the wrong input. Well, I measured it. Here's the numbers. Well, that's why you need to have 5 different instruments to measure the volume scattering function, and you find out there's really big error bars. We were looking at AC9 data today that was a factor of 2 difference, just depending on how you did the scattering correction. So once again, this ain't physics where you can buy a $20 voltmeter and you get voltages to 6 decimal places. We're doing well, to get sometimes factors of 2 agreement between models and one instrument and another instrument and so forth. That's just the way oceanography works. But that lack of accuracy there leaves lots of room for improvements and plenty more PhD dissertations to come out of getting better ways to do things. Okay, yeah, Miriam.
You could maybe measure like by study and then extrapolate or something.
Yes and no. The problem is if you measure, let's say this, and there are instruments, for example, there's the BB3, I think it measures like 3 different angles here, like 90, 120, and 160 or something. And then you can fit a curve, and if you have some kind of model for what it looks like, you can fit those 3 points and extrapolate them back. Well, that'll actually give you good results in this range, but by the time you've extrapolated back here, you're probably going to be off by an order of magnitude or 2 when you get to the small angles. And for your problem, maybe those small angles don't matter, but you really can't take 3 measurements here, fit a curve, and then compute the total scattering coefficient, for example, because it's very sensitive to these big magnitudes back here. So it depends on your problem. You may be able to do that. If all you need is the backscatter coefficient, which you're going to use for remote sensing, then it's great. You make a measurement here at, say, 3 angles, fit a curve. You can then get the backscatter coefficient, which is what goes into remote sensing reflectance. So that plus absorption. And then life is good, and you don't care if you're off up here. If you're doing a visibility study where that's really looking at light that's been forward scattered a lot of times because you're looking at this distant mountain and you're looking at the light from the mountain that's been scattered around, then you really need to know the forward scattered part, and you don't care how bad the back scatter is. So then you need a different instrument like the list that measures that first 20 degrees, and then you're home free with your problem, but you're not doing remote sensing reflectances. Okay, Emmanuel is going to give you a detailed lecture on particle size distributions. You've already seen the figure like this from Colin. So here's what's called the, I've defined my little n of x as how many particles are there per cubic meter per unit distance or per unit particle size. So, and people usually talk about a volume equivalent particle if they have some irregularly shaped particle, but that's got its own problems. So anyway, here's the particle concentration, n of x. It's particles per cubic meter per micrometer of particle size. And here's the equivalent spherical diameter in micrometers. Well, here's colloids, viruses, heterotrophic bacteria, blah, 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 down to microplankton here up to the 50 or 100 micrometer in size. And in this particular figure generated by Darius Stramsky, this is fit pretty well by a power law with a -4 exponent. And Emmanuel commented, call these things power laws. You'll often see them called the Junge distribution. Well, Junge studied this kind of stuff only for the -4 power. So in this case, this is a Junge distribution. Hyperbolic would mean the power is -1. A 1 over x is a hyperbola. So anyway, in general though, it's a power law, and this exponent here, when n of x is proportional to x to the -s, s is usually somewhere between 3 and 5. And of course, if there's a phytoplankton bloom, you don't get this line, you'll get a bump here at the size of your phytoplankton bloom. And I think it's going to be really cool. Someday we'll be able to make this curve from the size of protons to the size of galaxies, and like a universe averaged particle size distribution. And will it still be a -4? I don't know. Once upon a time there was a big gap there where you have the size of planets or solar systems, and now we're filling in. There's all these planets out there. There's over 4,000 planets discovered now. So we're getting the data that if we go out here, there will be a point down here somewhere where it's planets. Okay, enough said there. Emmanuel's going to tell you all about this stuff next week, I guess it is, or today, whenever. The reason I'm showing you this is because scattering strongly depends on the particle sizes. And here's a figure to prove that. So this was Ensign John Gay, probably now deceased, was flying 25 meters above the sea surface, which unfortunately is just out of the picture here, and flying past an aircraft carrier at basically something faster than the speed of sound. So if you're flying an airplane 25 meters above the ground and you're going faster than the speed of sound, that's not a place to make mistakes. So that's why I figure he's no longer with us. But anyway, it's an amazing photograph. And think of right here, let's say there's a cubic meter, it's got a certain number of water molecules in it. So whatever that number is. And as the plane is going along, there's a shock wave coming off of the nose and coming off of the cockpit. When the air goes through that shock wave, the pressure is reduced, and that causes the water molecules to condense out and form a cloud. So as you go from here, a little cubic meter of water, you don't get much scattering. You have a whole lot of water molecules. As you go through the shock wave, they condense into a cloud, and a cubic meter of air right here has exactly the same amount of water as it does out here. The only difference is here you have a lot of really small particles, and here you have a smaller number of large water droplets. and it totally changes the scattering. And then as the air goes out the back, the pressure comes back to what it was before. The cloud droplets evaporate and you go back to water molecules, and there's not much scattering. So the only point of this is to really emphasize that scattering is strongly dependent on the size of the particles for a given composition and everything else. Okay, neat photo. And he got some prize for his photo there. Okay, so let's look at some data for actual volume scattering functions and phase functions. So here's this Petzold data, and there's another, let's see, I've plotted here. The Petzold data is red. There's a model we'll talk about in a minute by Fournier and Ferrand that does a pretty good job of fitting the Petzold data, and this is for a typical ocean waters here. Here's for air bubbles in water. There's this Petzold curve, and here's measurements of the actual VSF for air bubbles in water. Well, you kind of look at it and say, yeah, they're sort of the same. But really, remember, if we come out here, that's an order of magnitude difference. So if you tried to model air bubbles and scattering by them and their effect on remote sensing, etc., and you use the Petzold phase function, you're going to be off by an order of magnitude at some angles. Here it's way too small, or Petzold's too big, here it's too small, here it's too big, here it's too small. So these, oh yeah, whatever. Anyway, that's just what the phase function for air bubbles in water looks like. And Colin asked me yesterday, what's this bump at 80, more or less 70 or 80 degrees here? And I checked up last night. It's, oh, maybe that's who it was. Okay, so here's your air bubble in water. This is the water out here. You can get internal reflections here, and it may leak out here. And if this is at a little bit different location, you may have several internal reflections, and then it'll leak out. And I found the paper back from the 1955 where they looked at this little like leveling off and then it drops off, and they did ray tracing for different places where the incoming ray hit the air bubble, and sometimes it would like bounce around, say 5, 6, 7 times, and then it would leak out. And so there was kind of a limit here of having like 1, 2, 3, 4, 5, 10, an infinite number of internal reflections, and then it all dropped off after that. So that's what's going on with that. Here's some phase functions of oil droplets in water, and you can see they've also plotted Petzold's clear ocean and turbid harbor data. That's these dashed lines here. So at small angles, the oil droplets have much, much less scattering than the Petzold data. And then at large angles out here, here's one of the Petzold curves here, the other one's down here, it looks like. Well, once again, things are a little bit off, but in between, yeah, they're not too bad. But notice as the oil ages, so here's a curve when the oil droplets are a day old, a week old, 2 weeks, and 5 weeks. We're getting over an order of magnitude difference in the phase function as this oil ages, because it changes its chemical composition. The volatiles leave, the really yucky stuff stays behind. And also for any one of these curves, here's the 1 week curve, notice there's a significant difference here, not quite, maybe a factor of 5, as a function of wavelength, because the oil optical properties depend on wavelength. So on the other hand, in the mid-range here, there's not too much difference. So you might get away with picking one of these curves unless you were interested in the narrow angle scattering. Then you really need to get the right one. If you're going to just look at the backscatter part, they're all about the same. So once again, depending on your problem, you may or may not need to be really accurate on which phase function you picked here. Here's some water droplets in air. We looked at air droplets in water. This is the opposite. So here's molecular scattering like from the water, then the water itself, then here's the water droplets in air. And notice there's a very high peak here. That's due to diffraction around the water droplets. And there's also 3 different wavelengths shown here. And then in the backward direction, at sort of like 140 degrees more or less, there's a little bump here, and there's another little bump here, and finally right at 180, there's a third little bump. Well, this little bump is what's causing the rainbow, which is at sort of like 48 degrees or whatever it is. If the sun is behind you, you're looking the opposite direction of the sun, and out at 40-something degrees, you see the rainbow. That's caused by this peak here. When you fly home, look out the airplane window. You'll always get a window seat on an airplane so you can see what's going along. There's often, you'll see this thing called a glory around the centered, the sun's here, look going through your head, the 180 degree direction. You'll see this little ring of light there, which is not a rainbow, it's technically called a glory. That's this little bump here. And you'll notice right around the body of the airplane, it's a little bit brighter there, but with the brightest point blocked by the shadow of the airplane, that's this little bump right there. So the volume scattering function is parameterizing all these different processes. There's diffraction, there's reflection by the surface of the droplets, there's refraction through the droplets, there's multiple scatterings inside the droplets. All of that stuff is what goes into making the shape of the phase function or the shape of the volume scattering function. And the nice thing about it is you don't have to worry about diffraction. It's described by this little peak here. You don't have to worry about multiple internal reflections and refraction through the droplet and all that. That's what gives you these bumps here, but all you care about is there's a bump here and this is what happens, and these things depend on wavelengths, so the angles will be a little bit different for different wavelengths, and that's what gives you the rainbow. And there's the typical thing you see for describing light coming through a raindrop.
It's another nice little thing with the glory field.
Yeah.
Is that all little droplets do that. So if you look on a dew on the grass, and you look at the shadow of your head, you're going to see something like this. Does that look like anything you've seen before in like religious pictures? Basically, if you're looking at the shadow of your head, you're going to see a nice halo around your head. However, you look at the shadow of your neighbor standing next to you, you won't see that around his head. So you get this idea that you're the holy one, you've got this nice halo, your friend doesn't have this, and obviously he's a sinner of some sort.
Yeah. Yeah, you'll never see a halo around my head, that's for sure. Yeah, there was a philosopher, I don't remember, I think it was Hegel, that observed the halo around his head and decided that was divine sign that he was the world's greatest philosopher. Well, he just didn't know any optics, that was all. Okay, here's phase function for ice crystals in air. And now here I plotted, let's see, the dashed line is atmospheric haze particles, and there's, I think there was some, the plus signs are human liver tissue, and then there's, I maybe had, the dotted line, that's the Petzold thing, and then the solid line is for the ice crystals. Well, notice there's a big bump here, a big bump here in these forward scattered directions, and those are light passing through hexagonal ice crystals going through in different ways that generate either the 22-degree bump or this 46-degree bump here. And those are what lead to, if you have a cirrus cloud with ice crystals and you're looking at the sun and you get these spots